Okay, everyone, so I finally posted your exam locations so you know where to go. And they're right here. You just click on this exam schedule and it will tell you where to go. So this place, 149 National Soybean Research, is south and east of the main campus. I should post a link to that so you'll know where to go for people who are going there. And Wohlers and everybody else will be in Wohlers and DKH. So any questions on that? And the conflict, you still have time to sign up for the conflict. Sign up by Friday on Lawn Kappa. You don't have to present any documentation. Anybody who wants to, as long as you sign up before Friday at 11:59 p.m. on Lawn Kappa, can take the conflict, and it's in 1024 Chem Annex the same day. No harder, no easier. Okay? So that's the idea there. Then I also updated, if you scroll down further, the study guides, what your materials to study. They're right here for exam 1. And these are updated, and as I said before, they just cover chapters 1 through 15. And so what we're going to do later in the hour is we'll look over some of this. But before we do that, let's finish up the 2 examples in significance testing that we skipped before. So let's go to the document camera and do that before I start talking about the format of the exam and what it will cover and the best way to study. All right, so let's go to the document camera now. And the first missed example was on page 70 in your notes, chapter 12. It was the one sample z-test right here. Okay, and this is one that's similar. I should say this is like the ESP example. This is an ESP example, and it's like the ESP homework problem in the homework that's due tonight. That's homework 7. So it's very similar. So, so this is a well-known experiment. There's been many experiments to see if people have ESP, extrasensory perception. And this was one that was done at, well-known one that was done at University of California in Davis. And people who thought they had ESP took this, thought they could just somehow sense what this machine that used a random number generator to pick one of 4 targets. It was called the Aquarius, and they thought that they would do better than chance, that they that somehow they could sense not through any ordinary senses, but could just sense what the machine picked. So the subjects tried to guess which of the 4 targets the machine chose. And there were 15 clairvoyants, people who thought they had ESP, and each of them made 500 guesses, and so that was a total of, they guessed, 7,500 times. Okay? And out of those, they were right 2,006 times. So they weren't, they certainly weren't always right. But if they had no ESP and were just guessing, they'd be right 1/4 of the time, which would be this. So this is this difference between what we observed, the sum that they got, the sum total right, minus the expected under just random guessing is 131 extra correct guesses. And so the question is, let's do a significance test to see if you think that could have happened just by random guessing or not. That's the idea. You probably have an intuitive idea. Is that so unusual that it would be very unlikely to happen by random chance? Or is that just within the typical variation? You don't get exactly what you'd expect every time. So it's hard for us to do this just with our intuition, so let's just do it with, this is a good example of how important it is to use the statistics we know. Okay? So formulate in terms of a box model. Well, the null is the usual null that the effect we see is just due to chance. So it's the effect we see this extra correct guesses. There's no ESP. The extra correct guesses, these 100, this effect size we see of 131 extra, this right here, is just due to chance, variation. You're not going to get exactly that every time. And the alternative is, the usual, that no, it's not due. It's too big an effect. That effect is so unlikely to be due to chance that it probably happened for a reason. The alternative is it happened for some reason. It wasn't chance. So the extra correct guesses aren't chance. It happened for a reason. Maybe they had ESP or something else. For a reason besides chance variation, some other reason. Okay, so we have to make the null box, and this one's very simple. We know the setup. If it happened by chance, they were just guessing, and there was one correct out of 4. So that's what it looks like. There were just 4 tickets, and each time they just randomly picked one. They did no better than you'd expect just by chance variation. All right, and this is the null box, and this is almost like a gambling game. This is very easy. It's like a guessing game. Okay, so what happened? So then our n, our sample size, is what? How many guesses? That's our n right there. It's 7,500 total guesses. And now, as in all guessing games, is this going to be with or without replacement? They made 7,500 from here. And each time, there was a 1 in 4 chance. So, without replacement, unlike our surveys that are always, with replacement, it's with replacement, unlike our surveys that are always without replacement. Everybody knows that because look, after 4 guesses, there'd be nothing left. Plus, we always want to keep the chances the same in there. So we randomly draw 7,500 times, and what happens? Our observed sum, we're counting up all the correct guesses, is what? They got 2,006, and our expected value for the sum, we got it here, is 1875, and we could also, it's the same thing as n times the average of the box. And n is 7,500, and the average of this, you can see, is 1/4. And that's how we got that. And that's 1875. Okay, so that's what we have. And now, this is 1 out of 4. And now, what are we going to do? We're going to compute the z, which is going to be the observed sum minus our expected sum divided by what? Some standard error, and it's going to be for the sum. So the standard error, remember what the standard error of the sum is. Do you remember what that is? The standard error, this is important because you're going to not be given these standard error formulas. So let's pretend it's an exam, and now you have to compute the standard error of the sum. Well, think of it this way. Standard error is just like a standard deviation. So just write that down. But it's a standard deviation for a chance process. And it depends on how many draws you get, what your n is. So remember, it's either going to be times the square root of n or divided by the square root of n. Sum grows. You're summing things up, so your error grows. So this is the time where it's times the square root of n. That's your formula. So we've got to get the standard deviation of that box. and it's not given to you. And this is something else you're going to need. So you see a box like that, standard deviation, has ones and zeros, right? So you could just use this simple formula, 0.25, 25%, p times 1 minus p times 0.75, and that gives you this. And that's the same thing. It's a special case of our shortcut, where what do? We take the biggest number on the ticket minus the smallest, or just the absolute value of that difference, 1 minus 0, times the fraction. There's 4 tickets in there. The fraction that have one of the numbers on them, that's 1 times 3. And that's the same thing. So either way. Okay? So now we've got that. So now we know this. But so we got the observed minus the expected. Let's look at that. We have it right up here. This is our observed, and that's our expected. And we already know it's 131. And that's the 131. Now, before we calculate that, I want you to use your intuition and see what we're doing here. We know this is going to follow the normal curve because of the central limit theorem. We have lots and a huge n, and so it's going to look like very close to the normal curve. And now, what are we doing here? We're saying that as a z-score, this is as a z, we'd expect 0 in the middle. And as a sum, we'd expect what in the middle? 1875. And we know we have 131 extra guesses to 2006. And what we're doing when we do that, when we do this calculation, we're saying, yeah, we know it's 131 extra, but where do we place 2006 along here? Just by our intuition, we know it's up here somewhere. Is it around here? Excuse me. Is it around here, 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 here? So, like, just using your intuition, maybe you just should tell me what you think. Like, tell me where to stop. Just intuitively, where do you think it would be? Like there, 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 or you have no idea? I guess you have no idea, and that's why we need statistics, right? Because you really don't know. I would think, my intuition told me it would probably be around there somewhere. I don't know. It doesn't seem that unusual. But, and I think, I don't know, maybe some people have better intuition. I've been doing this a long time, and I still don't have very good intuition until I actually do the calculation. And humans generally don't about stuff like this. That's why we need statistics. So we're going to do this calculation. And we take 0.433 times the square root of 7,500. And we're going to get the standard error, which will clue us in. And that I got to be 37.5. So now we have 131 divided by 37.5. And we get 3.5 as our z-score. And when you see that, you know it's astronomically big. This does not happen just by chance. And that's, I don't know if you intuitively saw that. I didn't. So it's way, way out here. And so it's between, here it is. That's where, it's even further out, but I just want to draw it this way. Between 2006 turns out 3.5. So between 3.5 and negative 3.5 turns out to be 99.953%. So this tiny little thing that I drew much bigger than it should be, I didn't draw it to scale, this little thing right here is our p-value. So our p is equal to 100 minus 99.953 divided by 2. And that is only equal to 0.02 0.035%. Okay? About, yeah. Okay? That's not even, that's so tiny. So what do we conclude? So we know that our p is really, really tiny. It's approximately 0.0235%, which is less than 5%. It's less than 1%. So we could say that it's highly significantly. So we call the result, so it's highly significant. Highly, very highly significant. More than highly significant. Extremely highly significant. So there's overwhelming evidence against the null. Against the null that they were just guessing. I mean, it would only happen, what, about 2 out of 10,000 times, right? That's just very, very unlikely. So it's overwhelming. Does that mean we've proved they have ESP? Actually not. They were never, many experiments have been done and it's never been replicated. Okay, so maybe if you do 10,000 experiments and just report this one, well then that shouldn't be the real p-value, right? There are other things wrong. Some people say there were things wrong with the random number generator. Some people think that there are other things wrong with the experiment, that the people who weren't doing well they started with more than 15, and they told them each time whether they were doing well, and the people who saw they weren't doing well said, oh, it's not my day, and left. And then there were just 15 left. There were a lot of other problems, but maybe. It's overwhelming against the null. So it happened for a reason, but not necessarily ESP. Okay? So we conclude, the conclusion is that this didn't happen by chance, but it's not necessarily ESP. I'll just write that down here. Not necessarily ESP. There's lots of other reasons. Okay? So we didn't prove it's ESP at all. Especially when you get something like this, you replicate it, and with these same people, they couldn't. Okay, so it was something else. Any questions on that? But why I like it is I like you to think intuitively and see the usefulness of statistics. That it really helps because our intuition is not very probabilistically accurate. And the next one we didn't do was on page 78, so let's do that one. So this is a 2-sample z-test for percents. Let's write that down here. All right. So this was around Valentine's Day. Gallup asked a lot of love questions, and it asked 500 men and 500 women if they'd ever fallen in love. At first sight, if they've ever fallen in love at first sight. So, and 44% of the men said yes, and 36% of the women said yes. So is this difference in response just due to chance variation or not? So let's do a significance test. All right, so which of the following is the null? I want you to take a moment to try to think about this and answer it, because this will help you if you start doing this. Just take a moment, just circle something and see if you're right. All right, and what the null would be is that there's no difference in the population. In our sample, sure we got a difference. There's no dispute that we got a difference in our sample. there's a difference. But we're wondering if we did it again and took another 100 random people of males and females, would this difference hold up? In the population, is there no difference? That is always the null, is in the population. So H naught, the null, remember, is always about the population, not the sample. Okay? So our null would be what? Well, let's just think about it. Let's set up the null, okay? Let's think what it would look like, and then we'll answer these other questions. All right, so let's think about it. So let's think we'd have two null boxes because we have two samples. One would be the male population, and the other would be the female population. And it was a nationwide sample of all adults. So there'd be millions of tickets in both. Okay? Millions of tickets. One for every US adult. All females and all males. Okay, so that's the idea. Now, what's written on the tickets? All we're interested in is whether they answered yes or no to this question. So those who answered yes, we'll call ones. Those who answered no, zeros. So it will look like that. Now, the null is, in our sample, we drew out 500 from each, and we got a difference. But the null is that inside the population, even though we don't know the percents of ones, we don't know these, but what our null is, that they're the same. So that the percent in the population of males, for males who would say yes, is equal to the percent of females who would say yes. Okay? In the population. Maybe I should write that notation here, up here, just so you know, so you don't get confused. So this will just be notation. Usually we use Greek letters, but P in Greek is pi, and that's confusing because pi is also has 3.14. So I'm just going to call it P is the population percent, and we'll put a little hat for the sample percent. A lot of people do that usually. So that's for our sample percent, just so you don't get confused. So in the population, that's what it looks like, okay? So in the population, we think our null is that they're the same, of course. But now, what's our alternative? Now let's think about these questions. Suppose before looking at the results, you thought men and women would respond differently, just because they often respond differently to things, but you don't know in which direction. You're not sure. You just think they'd be different, but you really don't know who would say which would be more. Then, should H alternative be one-sided or two-sided? What do you think? One-sided or two-sided? Let's say you really don't know. You just think they're going to be different in the population. Which one should you choose to be your alternative? Two-sided, right. Two-sided because you can't specify a direction. If you don't know, you just know they're different. So then, if that was the case, it would be two-sided, and it would be what? What does it look like when it's two-sided? Just that they're not equal. We don't put a direction. That's the two-sided. Two-sided looks like the alternative, when it's two-sided, always has an inequality, not a direction. So in this case, it would be PM is not equal to PF. All right. But now, let's say F. Okay, so let's get the results. So now let's look at the results, and we draw what? N equals 500 without replacement for both of them, randomly drawn. And in our sample, we get what? We get P hat for the males equals 44%. That's the ones, right? And in our sample for the females, we get 36%. So now we see this difference, okay? Let's say we see it now. So now, after looking at the results, you believe males are more likely to say yes to this question than females. So now can we change this? Can we change this? Because now we see, because then we could get more significance. We would only have to look at one tail, and usually it's interesting to get significance. Do you think it's fair to, after looking at the data, to change this to a greater than sign? What do people think? Anybody?
No.
Why do you think not? It's cheating. It's absolutely cheating. It's called data snooping or p-hacking, and it's cheating, and lots of people do it, and you shouldn't ever do that, okay? So you keep, let's say, no, it's cheating. Data snooping or p-hacking. Okay, you want to keep two-sided. Two-sided. You cannot change your alternative after looking at the data. So don't ever do that, okay? Now, let's just look at this last one. You decide to repeat the survey to gather more evidence to see if men really are more likely to fall in love at first sight compared to women. So now, if you repeat it, you got these results, and let's say you want to do it again just to get more evidence. Now that you've seen this, is it cheating with new data the next time? What do you think? Should the alternative be one-sided or two-sided? What do you think? Anybody? What? One-sided, right. Now that you know more information, you might as well use it. So now you can change it. You have new data. So you can make a new alternative, as long as you make it before you look at the new data. Again, before looking at the new data. All right, so that's the idea. All right, so now we'll do this, and what would it look like? It would look like your alternative would be like this. It would be greater than. It has a sign. That would be your alternative. That's your new alternative, as opposed to this. Okay? It would have a greater than sign there. If your hypothesis was that that males would be less, then it would have a less than sign. Okay, so we're good there. So what do we need to do? We've got this, we've got this. Oh, so now, like you might be thinking, okay, now what do I need? You're always going to need these standard errors, and we can get them directly. The standard error, the sample percent, we can get it directly from there. Remember what it is. It's going to be the sigma of the box, which we'll estimate from that, SD, over square root of n times 100. So in this case, we're going to use this as our estimate for the ones, the yeses, and we're going to use this here. We'll estimate. All right, and we get 0.44 times what? 1 minus that, right? That would be for the zeros. So that's 0.56 divided by the square root of 500 times 100. And that's our answer for this. And I got 2.22% for this one. And we'll do the same for the females. So you can get females, and they'll be the square root of 0.36, and I have to make it add up to 1, so it's times 64 over the square root of 500 times 100. Now they have the same n. I just want to ask you, which one do you think is going to be bigger? The one that's closer to 0.55 has more uncertainty. So this should be smaller. We should get a smaller standard error. It's more lopsided. So the standard deviation is less. You're more likely to get zeros here than here. Okay, and we got less. I got 2.15%. Very similar, but less. All right, so that's where we're at. Any questions so far? All right, so now what we're going to do is we remember what our z is. And if you forget, we have a chance process here. So what are you going to think? Okay, you're always going to think observed minus expected over some standard error. And what are we looking at? We're looking at differences. So it's the observed difference between the two. We have two samples, minus the expected over the standard error for the difference. Right? So our observed difference is what? 44% minus 36%. That's our observed, that 8%, minus our expected is 0 difference. That's why we can just cross that out. It's always 0 for the problems we're looking at. In this course, our null is it doesn't have to be, but in this course, the ones that we've been looking at, we're doing the strict null, which was always 0. Okay? Over. Now, standard error for the difference. How are you going to remember this? Well, remember the Pythagorean theorem. You're having to sum these two things. So it's going to be the square root of this one squared, we've already calculated, plus that one squared. These are percents, plus 2.15 squared. And the percent cancels out, and we get, well, I'll just say 8% over 3.09%. That's what it is. And then the percents cancel out, and we just get this pure z-score, standard units, that's equal to 2.59. Now you should look at that, it's a z, so you should know that's pretty significant. That's far out on the tails, whether we did one-sided or two-sided. You should know just by looking at it. Okay? Does that make sense? I crossed off this 0 because our null is that these are the same. There's no difference, right? It's 0. This is our null right here. It's the strict null, and for all these problems, when we're comparing two things, it's always going to be 0 for the problems we're doing in Stat 200. It doesn't have to be, but for the ones we're doing, it will be. All right, so now what's my next step? Y'all know what the next step is, right? A normal curve, and you're going to have to be drawing this on your own. You're not always, but you'll have the table, so we can do this, and we'll just draw a picture. All right. And we just it just boils down to between 2.59 and negative 2.59, we're going to get a middle area. And I got 99% at the back of the book about that. All right. So now we did the P for the 2. So P for two-tail test, because we didn't know whether we were going to land on this side or this side before we looked at the data. We didn't know. Remember? This is 0. We didn't know if we were going to get higher than 1875 or lower. We just thought it was going to be different. Not 1875, what? The difference we thought was going to be either males were going to be more or males were going to be less. We didn't know. Okay, and it doesn't really matter which way you subtract it here because we're doing a two-tail test. So it's just 1%. That's both tails. Okay, what if we did it for the one-tail test? It would just be what? If we did decide to go with that one, and we didn't look at the data first, then it would just be half of that. Does everybody understand that? It would just be this tail, which would be 0.5%, which is even more significant. And when people have that 5% cutoff, and it's hard to get published without that, if you get a 6% result one way, you're really, really tempted to say, hey, I had the one tail. I really have a 3%, so I can get it published. It's significant. And that's why almost all journals don't trust and say, hey, just do the two-tail test for everyone, even if you logically have enough information that you could do a one-tail test. And software too. So that's the idea. Does everybody understand? We can write this P for one-tail test is always what? It's the middle, it's going to be the middle area minus 99%, but then it's just one tail. So we divide by 2, and then we'll get 0.5%, which is more significant. That's very highly significant. Any questions? All right, and so I think we've finished everything. The one thing that I never filled in was some probability problems that I'll post in case, because you'll probably use them for studying. Wherever they were, I'll post them and put them, here they were on page 35. So on that lecture, I can post that. So you'll have that. On the calendar, I'll put it for page 35, just so if you wanted to review that. All right, now what else do we need to do? So let's look, for now, let's go and let's go to the PC. And PC. And here, the first thing let's do is let's look at these, what you need. Let's look at the top. It says no formula sheets or graphing calculators may be used on any exam. So be sure that you have a calculator, test it out first. You can't have anyone that connects to the internet or can store information. I like using those graphing calculators because I'm used to them, and I wish you could use them, but too many people are cheating with them, so we can't anymore. So be sure to bring a calculator, but you can't have a graphing calculator, and you can't have your phone calculator. All right, now, yes? You can use TIs, but not like TI 80, not TI Inspires, not 80, that 83, 84, 85, 80, any of those. But the ones like the 30, I think that like the ones I recommended on the syllabus are good, okay? Like you can just go here, and there's a recommended calculator right here. This one you can look at. That one for sure you can get. Okay, so let's go back to the exam schedule. And so now, and no formula sheets. So does that mean you never get formulas? No, if you get formulas, they'll be included in the exam. And for this exam, you're not getting any formulas. So these right here are the formulas that are not, you're not getting any formulas, but these are just sort of a summary of what did I do here? Wait a minute, this is for, I scared you. I'm so sorry. You're probably going, what? Oh no, I don't know any of this. I'm so sorry. Let's get out of here. I did this for, I want exam 1 formulas. Now now it looks much better, doesn't it? Okay. That was for exam 2. Okay. So let's just make sure you know what I'm talking about here. So yeah, you do need to know how to do the standard deviation the long way. It's all multiple choice. So you're probably wondering, well, if it's all multiple choice, can't I just do it on my calculator? No, because they might ask you for steps along the way. Like what's the missing deviation? Or here, like steps along the way so that you'd have to know the procedure, okay? It is all multiple choice. So it's all Scantron graded. So that's how it's going to be. You're just going to be filling in bubbles on the Scantron sheet. And the shortcut standard formula you need to know too. All right. Now, obviously, you need to know how the z-score, value minus average over standard deviation, and the basic probability rules. So, and then these expected value and standard errors. The standard error, I said, the easiest way to remember it is SD and square root of n. That's what it involves. And here you multiply, and for these two you divide. And it's on page 14 of the study guide that's also posted here, is a good place to look for the standard error formulas. And then look at so here we started off with descriptive statistics, and it was just value minus average over standard deviation. That's when getting a z-score, and we did normal approximations if the data themselves followed the normal curve roughly, like heights, weights, IQ, ACT scores, etc. Not for money, not for things that didn't. Now, then we moved on to random variables, numbers generated by a chance process. And now we have the same thing, what we expected value, what you'd expect to see, and the sampling error. You get a different thing every time. So that's why it's called error. It's sampling error instead of just a standard deviation. So, and then you have these confidence intervals where you need to do what? I didn't write it down here, but you remember what you do. The confidence intervals, when you you're trying to estimate a population from a sample. So you take your sample point estimate, your sample statistic, and you add and subtract a margin of error that corresponds to either the z or the t curves, is what we looked at. Like a 95% confidence interval would be 2 standard errors for the z and a little bit more for the t. So you need to remember how to get those critical values. So review that by looking at the tables. And then we moved on to these significance tests, and we have the one sample z and t test, and they look very much the same. The only difference is the standard error is tweaked for the t, and this is you could do that, or you could it's bigger, and SD plus is bigger. And it's bigger for both of them by this factor. All right, and then we did the 2, and then you have to look on the t curves for the t. And the t curves, here's what you need to remember. T curves are fat in the tails. They have fatter tails, flatter in the middle. More uncertainty. It's when you don't know the SD, you have more uncertainty, so you're going to have bigger error bars, wider confidence interval, more error. Bigger p-values, fatter tails. The z gives you, the z is simpler, but people don't like to use it as much because it's less conservative. And sometimes they think, oh, if you did a t-test, you wouldn't get significance. And you did the z, and you got significance, and we don't trust it. That's the political reason behind it. Whoa. Glad you brought me those. You knew those paper towels. All right, so now, any questions on that? And then the 2 sample Z and T tests, and you just get, we just went over that. It's basically the Pythagorean theorem for the difference. And then the degrees of freedoms are super easy. It's n-1 for the t-test, and it's n-1 for the 2 sample 1, 2. You just use the smaller sample size. So that's basically it, your formulas. And now let's talk about the exam. All right, so let's go here to, back to here. And so I posted this exam that's a revised version of Spring 2019 exam, and I tried to make it pretty similar to how you see it now. And so this is updated. It just goes chapters 1 through 15, and it has 61 problems, 9 pages. Now, the real exam might be a little bit longer, because this originally covered 1 through 16, 1 through 18 when these kids took it. So I cut out some of it, added a few, but I'll probably add more. So I would expect somewhere between 65 problems and 70 maybe even. So a little bit longer. But this is will be very similar. Now I don't want to go over this with you, but I want you to, because this I want you to take as a real exam. Like with, so I don't want to go over it, just so you'll know what to expect and can gauge it. Okay? So you're going to do this one on your own. I just want to show you it's there and the key is there. So I don't want you to look at it yet because it's great practice. So I can't stress enough to take this after you've done your study guide, which is much, much, much longer. So you're prepared. After you've done all the homework, you know, you still have homework that's due Sunday. So get that out of the way right away. Get 7 is due tonight, and I'd just do 8 right away, and then just start studying with the study guide. And the study guide is extensive and long. So, for example, and it tells you what to look out for, what the main ideas are for each chapter. It goes through the whole thing and gives you tons and tons and tons of practice. So it's way, way longer than what, and of course, not everything that's on here is going to be on the exam. It couldn't possibly be, but it just gives you tons and tons and tons of practice. Okay, and here, for example, it tells you what formulas you need to know and what you need to know before each chapter. So I think that's good, and go through it, and you don't have to do every problem if you know how to do them all. If you feel like you know them, but I would look at every problem. And it goes on for pages, so. Okay, and then there's a key, too. There's an extensive worked out key with explanations for all this. So after you do that, you're going to know what areas you have problems with, and you can repeat the homework. You can go to Lon Kappa, and every single homework assignment that you'll have 1 through 8 will be in practice folder, and you'll get new numbers for many of them. And just do the ones that that you feel rusty on, because I am going to probably pick some of the classic homework problems or something like it to put on the exam. You know, I'm going to try to make it pretty simple numbers, but there's going to be, just test your understanding is what I'm going to do. So that's the idea. And so everything you need is here. And do this as a real exam. Allow yourself 90 minutes. Do not peek at the key. I can't tell you how important this is. Psychologically, there's been experiments on this, and the theory behind it is that you need to develop pathways in your brain where you store information. So in order to be able to succeed on a real exam, you have to practice in a real way, right? Like if you were going to run a race, you have to practice. You can't stop all the time. But the idea, particularly with an exam like this, is that you really do have to be able to understand some of the concepts. And I know you understand them probably, but you have to be able to retrieve the information. So you have to know where you stored it in your brain and how to retrieve it. And if you take an exam like a real exam, it develops those pathways. You feel like, oh, what? I know this. And if you peek, it just defeats the whole purpose. So even if you don't know it, go through the whole thing and just rack your brain as if it was a real exam, and it will help you. And if I have a chance, I'll revise last semester's exam, so you'll have another chance to do another exam. So I'll try to get that up there, but that probably won't be up there till Saturday or Sunday. So because right now it has a lot of other stuff in it, last semester's exam. But if I revise it and add some stuff to that, or that could be another practice exam for you guys. So you'll have 2 of them. And that's the absolute best way to study. In fact, even if I can't make it a full exam, I'll still post it, because you need more practice on real exams. So even if it's shorter, it will still be worthwhile if you take it as a real exam. So I will definitely do that this weekend, and I'll send you an email when I do that. And it will have a worked out. This key is completely, oh, look at that. Why did that happen? I just scanned it, but it's all worked out. You can ignore that. My scanner must have. I'm sorry. Oh, well. You can still see it. It's fine. All right. So it's all worked out there. And you're going to have a cover sheet like this, too. So might as well look at it, read it now. And the other thing is, so what about office hours? Well, office hours for the exam. So it's just going to be our usual. Let's just go to our syllabus. And I strongly recommend you come to office hours if you, they're right here, 2 to 5. So they're today, Friday, and Monday, 2 to 5, every one of those days. And don't wait till Monday because we'll be jammed and probably it will be chaos. And right before an exam, everybody's going to be nervous. And so come on. It's better to come on today or Friday. I mean, look, it's 3 hours. You can there'll be lots of TAs there. You'll still get help on Monday. And it won't be so crazy, but so definitely come if you have a question. But the conflict starts at 4:30, so I'm going to have to leave office hours at 4. So, but I'll be there 2 to 4, and the TAs will be there too. And the TAs are amazing. Not only they're graduate instructors, but we have undergrads who are phenomenal, who took Stat 200 and did great in it and can really help you. So, no R this week. Let's just look at our schedule, again, our calendar, and see what's up this week. All right, so here we are. Whoops. Sorry. Okay. There is one pre-lecture due, Chapter 14, 2 sample Z-test. Here's your exam conflict. That's due on Friday. This is due on Sunday. And these are your 2 homeworks. Do those as soon as possible. And then it's all study, okay? After that, get that out of the way. That will really help you. And then just start studying here. And we do have class the next day. But no homework due till there. So, any questions on anything about the exam? Of course, no notes or books or anything. Multiple versions. We always have multiple versions, so don't even think about cheating. They look alike, but they're not. If you haven't been in Stat 100 or had an exam I've made before, I always do this, always multiple versions, and always they're hard to tell the difference. They're just something slightly different, and the answers are different. And we can tell. It's almost like giving us a signed confession when we have particular ones that really stand out. There's no, that you just wouldn't get otherwise. So let's make it a cheat-free year. It's not worth it. Absolutely not worth it. Just do your own work. And you'll have plenty of time because it's an hour and a half, and I try to make it plenty of time. So, and you can email me if you have any questions. So, go ahead, question? How many questions? I haven't written it yet, but I expect it to be about 65, no more than 70, probably around 65. But they're really little questions. I mean, it's not like 65 separate. That's bubbles you fill in. Not 65 whole problems. Oh my gosh, no. No. Like each thing is like with or without replacement. That would be one bubble. You know what I mean? Like each question has a whole lot of parts. And lots of, it's not going to be a whole lot of calculations. Just a little bit longer than the practice exam I have up there now, which is 61, you can see. Maybe it'll only be 61, somewhere around there. All right, any other questions? All right, well, what time is it? Let's see, we can just, Oh, good. It's early. I've been keeping you so long. So why don't we just, if you want to stay and ask me questions about anything individually, I'll just be here for the rest of the hour. But I've been keeping you for the full time for the last 3 lectures. So just, that's it. And stick around if you want to have any questions on anything.